Good evening. I am so excited to see so many of you here tonight. The McLean Science Lecture Competition honors legendary former science faculty member Dr. Peter McLean and his passion for communicating his love of science, and especially our natural world. Dr. McLean worked at St. Andrews for more than 2 decades, teaching biology and environmental science, helping students explore the natural world, and encouraging sustainability. Dr. McLean continues to serve as a role model, staying engaged in local, regional, and national conservation and sustainability initiatives. I want to thank my colleagues in the science department for helping to make this happen. Much of this started with inspiration that they provided in their classes every day, and I'm grateful for the additional time that they spent coaching the participants, listening to auditions, and being judges here tonight. This was one of our most competitive years for the McLean Science Lecture, with a record number of students auditioning, and so I briefly want to recognize all of the students who participated. So if you auditioned, if you could please stand now to be recognized. You all can stand too. As the finalists, you guys can stand too. Finally, I want to commend our 4 finalists for the work they've put in over the last few months. Everything you hear tonight is something that these students learned outside of the classroom in their formal science studies. While I hope you learn a lot about the specific topics they're going to discuss tonight, above all, I want you to recognize the opportunity you have every day to explore your passions and interests. I hope these talks encourage you to inspire and engage in your own research and self-study. You don't have to wait until you're in the classroom to learn something. Thank you all for being here tonight. Ready?
Quantum computing, solving big problems with a tiny solution. Imagine being able to decode every message ever sent on an iPhone, ever. Every text, every email, every voicemail, every Google document, every Word document. And imagine being able to do this in seconds. Imagine being able to simulate the world that we live in down to its very smallest particles so that they can come up with new drugs, new pharmaceuticals, and cures to dangerous diseases. Imagine being able to encrypt data in such a way that it is virtually unhackable. And imagine being able to do this with the stroke of a keyboard. That and much more is possible with quantum computing. Many scientists believe that if the progress and the research continues at the rate that it is, we will be living in a fully quantized, fully changed world in 20 to 50 years. But first, what is quantum? We hear that word a lot in Marvel movies or the Big Bang Theory. It's thrown around and no one really knows what it means. It's very esoteric. But basically, quantum mechanics studies how really small materials like electrons, atoms, nuclei, photons, can exist as both particles, which is just tiny bits of matter, and waves, which is a transference of energy. This is called wave-particle duality, and it's what makes quantum computing and our very world operate. Now, there are 3 principles of quantum mechanics that happen because of this particle-wave duality, and they are superposition, entanglement, and decoherence. Superposition is the ability of an atom or another quantized object to exist in multiple or mixed energy states at once. Think of an energy state like if you were on a ladder. If you were on the ground of the ladder, you're at energy state 0, you have no extra energy. And if you're at the top of the ladder, you're at energy state 1, you have some extra energy. Superposition allows you to be at both the bottom of the ladder and the top of the ladder at the same time. This is really interesting, but it isn't useful. It only becomes useful when you add the principle of entanglement. Entanglement is the connectedness of multiple particles in superposition. That means that if I have a particle in superposition here on Earth, and it is entangled, the particle could be anywhere. It could be galaxies away, it could be on the moon, it could be right next door. Whenever you have that first quantized object in superposition, if you measure it, you will always measure the second one. They will always have a correlation. It's almost romantic. It can cross galaxies. The last principle that we need to know is decoherence. Decoherence is the collapse of a particle in superposition into a single state when measured. This happens whenever you finally look at the system. And if you measure one object in superposition, you measure all the other entangled objects in superposition. This can happen on purpose when scientists are finally ready to get the solutions to all of their hard equations that they put in. Or it can happen by tiny affectations in the environment. And that makes superposition and quantum computers very unstable. They can decohere very easily. That's cool. Hopefully we learned a bit about quantum. But how on earth could that ever be a computer? To understand that, we have to understand what a computer is. A computer, in its simplest form, is anything that takes inputs, stores them, processes them, and then gives you outputs. Classical computers, like the one I'm running this presentation off right now, do this through binary digits, or bits, which are series of zeros and ones that go through logic gates to give you outputs. Quantum computers use qubits, or quantum bits. Qubits are like bits in that they can be in a 0 state or a 1 state. They're special because they can also be in a superposition of those two states. This means that if you have two classical bits, you have two pieces of information. You have whether the first one is in 0 or 1, and whether the second one is in 0 or 1. If you have two qubits, you have 4 pieces of information. You have the likelihood that when you measure the system and decohere it, the qubits will fall to a state of 0, 0, 1, 1, 0, 1, or 1, 0. That means that for every n classical bits, you have 2 to the n power of information with a quantum bit. This is exponential, but it's difficult to understand how large this number is. That means that if you have 600 entangled qubits that when measured, they would all decohere at the same time, you have 2 to the 600 pieces of data, or 2 to the 600 equivalent classical bits. 2 to the 600 is more than there are particles in the universe. Quantum computers can do huge amounts of calculations with these. But how does it actually do those calculations? What actually happens? I like to think about it like you have 2 stones. Say you throw them into Knoxontown Pond. They're going to have ripples that they'll ripple out. And these ripples are going to interfere with each other. Sometimes 2 ripples will meet at a high point. Sometimes they'll meet at a low point. And sometimes a high point will meet a low point and they will cancel each other out. The same thing happens with entangled qubits. Our stones are our 2 entangled qubits. When you have the data and the probabilities, the more qubits you add, some peaks will get bigger, and that probability will get more and more likely. And some troughs will get lower. Those probabilities will become less and less likely. And some solutions or probable answers will cancel each other out through these waves. And that means that quantum computers don't give you an answer like a normal computer does. It gives you probabilistic answers, answers that would probably be correct. And this can limit the number of solutions from huge numbers down to very, very set values. Another way to think about this is think like you're in a maze. What a classical computer would do was try every single solution one at a time. In a normal maze, that might work, but in mazes with huge amounts of solutions, that will take forever. It can't be done. A quantum computer, on the other hand, will rise above the system. Some people have a misconception that what a quantum computer is doing is it's trying every single solution at the same time. That's not what's happening. The quantum computer gets to rise above the maze and sees which solutions are the most probable or the most likely to getting you out of the maze. And with every entangled qubit added to the system, you can see more and more of the maze, and probable answers become more and more probable, and improbable answers become less and less probable. That's some pretty cool theory. It's really cool theoretical information, but how could that on Earth be synthesized? I would like to start this by saying a computer, as I said before, is anything that can process data. The first quantum computers were some of the first quantum computers were actually made at IBM in vials of chloroform with isotopically enriched molecules of chloroform that became entangled and would talk to each other in quantum words, and they could factor 15 with that. So quantum computers don't have to be like we view them today, like how this normal computer is right here. We have since left that technology mostly behind because people figured out that maybe chloroform vials aren't the best computers you could make. But there are thousands of types of quantum computers out here, and the two that I'm going to highlight are just some of them. The first that I'd like to highlight is a superconducting quantum computer, which is the one on the left. And the other one is a trapped ion quantum computer. A superconducting quantum computer uses circuits of electrons that run through chips and stimulators, and these electrons act as the quantized object that become entangled. And they run through logic gates just like a normal computer to give you outputs, and scientists will set the electrons at certain currents so that they act like a quantum thing and have those waves of interference. This is really cool, and maybe you can't tell on the screen, but a superconducting quantum computer is bigger than this room. It's bigger than Engelhard. And it can do calculations so quickly because it can limit the number of solutions from like almost infinite to very few answers. And it's the fastest type of quantum computer there is. The problem is that to do this, it's very, very fragile. And with any little shift in electron current or electron spin, a qubit can decohere. And if one qubit decoheres, it can corrode the entire system. Because of this, superconducting quantum computers have to be kept at almost absolute 0-degree temperatures. It's approaching negative 475 degrees. So we're probably not gonna have a quantum computer here at St. Andrews. That's probably not how we're gonna spend our science budget. A trapped ion quantum computer, on the other hand, is much less fragile and can be kept at much cooler, much warmer temperatures. But they are also much slower and cannot do as much calculation as a superconducting computer. A trapped ion quantum computer uses ions that are in vacuums and set to certain spins by lasers to become entangled and do the quantum logic gates. And to get the final answers, they will send the trapped ion quantum computer basically through an MRI machine, or a version of an MRI machine that uses electromagnetic fields to eventually measure the system when it's ready. So where has this field been? How old has it been around? Who made it? What has been going on? Basically, Richard Feynman first proposed the idea of quantum computing in 1981. That means even the theory of this field has existed for less than 50 years, and the fact that we have practical operating quantum computers doing calculations is really shocking in that short amount of time. Feynman, who was studying quantum under Schrödinger, wrote a paper that in order to simulate quantum physics and how the world actually really works at its smallest level, that will have to run off of a quantum simulator. It will have to be actually made of quantum. And he wrote some algorithms and he put that out into the world. And they were like, okay, cool. But no one did anything with it. People forgot, left it a little bit behind. They're like, that's no way that's possible. Until 1994 and 1995, when Peter Shor and Love Grover, respectively, reinvigorated the field by creating new algorithms and new practical applications of a quantum computer. Peter Shor basically showed that if a quantum computer could actually be synthesized, it could have access to every single piece of government data that exists in the world. All of our intelligence corporations would fail with a quantum computer. They could be hacked in seconds. And this meant that governments were spending so much money. They started spending tons of their money on quantum computing. Russia, America, China, they'd come out of the Cold War, and this is what they were spending their scientific budget on. This meant that the field really started bursting open. And in 1999, Yasunori Nakamura created the idea of the superconducting quantum computer, which we went over before. And a superconducting quantum computer uses chips and silicon just like a normal computer in a really different way. So it suddenly became all the more practical. Quantum computing might actually exist. It could actually work once Yasunori Nakamura entered the field. So people were getting really, really excited. And then in 2005, researchers at Yale came up with error codes that meant that even if one qubit in a superconducting computer accidentally decoheres, they could set it back without having to remake their entire quantum computer. Things just became more and more possible. So what's new? Where are we at now? In 2016, the quantum computer and quantum computing power was added to the web by IBM so that teachers and researchers and lab workers and students could all be able to play around with this new computer and all be able to run theories and run algorithms and try things out. So if you think that the field reinvigorated itself in 1995, in 2016, the amount of papers and scientific minds that entered the field was so much more. You didn't have to have access to a negative 475 degree temperature room anymore. You could just have a normal computer and a will to learn. In September of 2025, a team at Caltech, the one on the right there, created the largest superconducting quantum computer ever with 6,100 entangled qubits. I said before that 2 to the 600 is more than there are pieces of particles in the universe. 2 to the 6,100 is impossible for us to wrap our minds around. This is more than there are particles in the universe have ever been and probably ever will be. This number is huge. The amount of computing power that quantum computer can do is shocking. And then in June of 2025, Google came out with their quantum Willow chip, and that's that one, and that's their version of their superconducting quantum computer. And that could do calculations in 5 minutes that would take a normal classical computer 10 septillion years to complete. 10 septillion is 10 with 25 zeros after it, and is longer than the universe has ever existed. That is how much quantum computers are changing the world. Now, I started this talk saying that quantum computing would be able to read every single text message that you ever sent, ever. And here's why. Google and most encryption techniques use something called prime factorization to hide their keys and encrypt their keys. Prime factorization is basically taking 2 or more really, really large prime numbers and multiplying them together to create a key that cannot be factored by a normal computer. It would take thousands of years, many, many lifetimes for that to ever be factorable. A quantum computer could do that kind of calculation in nanoseconds. I mean actual nanoseconds. But there's a bright side. Quantum computers can also be used to encrypt data. They can do that because, like I was saying, whenever you measure a quantum system, you decohere the quantum system. It no longer is in superposition. So that means if anyone is spying on a key transference or is seeing your key, that means that it will automatically decohere, and you will know that your key has been intercepted and you can't use that encryption anymore. You can have quantum safe encryption if you have the money to pay for it, so it shows a new world. There are many, many other applications that I'd be happy to get into over questions. These are some of my references. Thank you. Any questions?
Thank you so much, Alice. We've got time for a couple of questions.
I'm just kind of wondering how, like, the quantum computer is able to manipulate the qubits into solving problems. Like, what algorithms does it use, kind of?
Yeah. So superconducting quantum computers use logic gates like a normal computer, and they run the electron circuits through the logic gates to get the waves of probabilities. But basically, in order to set the qubits into a system that can be measured and can get you the sort of answers that you want, you use like lasers to set them, like these really special lasers. They set the qubits at certain spins so that they are in the like the formation that you want to give you your answers. If that makes sense.
Other questions?
My question's about like accessibility. So I know you mentioned that like recently quantum computing has become more accessible, but to what extent is like the high level of quantum computing accessible for the public, and how do you think that that's going to change based off of like the research that's being done?
Well, quantum computing, as I was saying, is a field that's relatively young. And so most of the science and the technology up until this point has been research and experimentation. And I think from now, like starting around now and kind of moving into the future, there's going to be a shift away from just research and into applications. And because of this, I think quantum computers are going to become more accessible because they're going to be a larger part of our lives. Like they're going to be like actually doing things instead of just researching the technology, if you know what I mean. And the actual quantum computers are very hard to get your hands on. You have to be like pretty smart and part of really selective teams at like IBM or Caltech or MIT or Google. But because it's available on the cloud, you can like play around with it from a distance. So anyone can do that.
Alice, your presentation was amazing. I was just wondering what you meant by saying the world could at one point become like quantumized. Like, what does this entail, and like, what are some like everyday applications of quantum computers that could take over like ordinary functions of normal computers?
Well, what a quantized world could mean is that these quantum computers can simulate the way that atoms and elements are like interacting at very, very small levels. And I think that is you can use that to create pharmaceuticals and drugs. So I definitely think the biomedical field is going to get really revolutionized, and it's going to shift towards using quantum computers more than normal computers and that type of experimentation, because they'll start plugging it into quantum computer. And Yes, I also think that encryption and decryption is really going to change, because we have this view that things that we do on our computers are relatively safe. And I think that as quantum computers become more accessible, it's going to become even more clear than it already is that everything we do on our phones is unsafe unless we are able to pay for and access quantum safe encryption. So I think things could get hacked more, or you'd have to pay more for data security, things like that.
Hi, Alice. You obviously mentioned hacking and data encryption and kind of things like that. So as much as this could be renovational to society, how do you feel like there could be any ethical concerns to maybe the privacy or the safety of individuals? Because with every great advancement, there comes a lot of problems that could be within context.
Yeah, I would say that there are, of course, ethical concerns with quantum computers, especially because most of the teams that are making the quantum computers are actually working for certain governments, and that means they have certain agendas that they want to achieve. They're doing this not just for the benefit of humanity or for the benefit of science, but to actually get someone else's data and hack their nuclear systems, things like that. I definitely think that any new science really can be used for good and bad things. You can use a computer for bad things, and I think that you can use a quantum computer for bad things, just at probably a larger scale.
Thank you so much, Alice.
Hi everyone, thank you so much for coming out tonight. Today I'll be talking about hip dysplasia and whether or not stem cell therapy can potentially replace the need for surgery for patients with this condition. Last soccer season, I was experiencing a lot of hip pains, some lower back pain, and a lot of difficulty with walking and running. At first I brushed this off thinking it was nothing because I hadn't previously injured any part of my body that could result in this pain. But it got so bad that over the summer, I went to a doctor and I got diagnosed with moderate to severe hip dysplasia. I hear many of you giggling, and yeah, that's an actual snap that I sent from my doctor's office when I found out that I needed surgery. Basically what they explained to me was that hip dysplasia, or DDH, developmental dysplasia of the hip, is a malformation of the hip joint in which the hip socket and the top of the femur don't fit together properly. That results in inflammation and thus pain, and can lead to osteoarthritis if left untreated. At the time, I could barely even spell the word dysplasia, let alone be able to process that my hip pain, which at the time was kind of just a minor inconvenience to playing soccer, could ever escalate to me needing a major reconstructive surgery, or worse, a hip replacement by the time I'm 30. My parents and I decided to try and delay the surgery, so right now I'm getting physical therapy, which includes strengthening glutes, core, and the deep anterior hip flexors. And I'm going to delay the surgery, hopefully, until after I graduate high school. How is hip dysplasia developed? Well, there are many genetic factors that go into this because hip dysplasia is a congenital disorder. That means that it's present at birth. There are many factors that can cause hip dysplasia. For example, how a baby was born, the breech position they were inside the womb, even how they're swaddled outside the womb can determine whether or not a child might develop hip dysplasia in the future. It's actually more common in girls than boys, and there are many other genetic variances, for example, collagen production, that can play a part in whether or not you might develop hip dysplasia. 10% of infants are actually born with some sort of hip instability, but only 1% of babies are formally diagnosed and treated with hip dysplasia. This is because at birth, the hip joint is essentially soft cartilage that eventually hardens to bone, but during this time, it's very malleable. And if during that time the ball and socket don't fit together properly or something happens, then that child might end up with a hip that looks something like this. This is obviously a very severe case. As you can see, the socket is barely existent, and the top of the bone obviously doesn't fit properly inside of it. This is an x-ray of my hips versus a set of healthy hips. When I first sat down with my doctor, he basically looked me in the eye and said that I'm screwed because my hips are 25 degrees off rotation. But as you can see from this x-ray, the socket on my hips is a lot more shallow than that on the right. Here's a closer look of it if you want to see. I highlighted in red the part that is completely left uncovered by my hip socket. That means that my hips are highly unstable, and as a result, my hip flexor muscles, which is this group of 5 muscles right here, have to overcompensate to be able to provide stability to my everyday walking or running or playing soccer. And because of the injury, my body automatically activates an immune system response, triggering acute inflammation in an attempt to heal or get rid of all the damaged cells. The inflammation response here is overactivated, which causes damage to the normal cells and leads to pain. This also impacts my mobility, which means that I oftentimes experience pain while playing sports. And if you see me walking around with a little bit of a limp, that's probably what it is as well. In addition, part of the hip flexors extends to the lower back, which would explain why I was experiencing pain in those areas when I was playing soccer. These are 2 very common fates of people with hip dysplasia. They can develop a hip labral tear, and if left completely untreated, can develop osteoarthritis. Claire Walker, I see you cringing at the photos. Oftentimes it's because the friction between the hip socket and the bone causes inflammation and wears and tears on the hips. I know, kind of gross. But the hip labral tear is when there's damage done to the tissue holding together the ball and socket. And osteoarthritis is usually what happens when there's damage to the actual cartilage or the cushion part between the ball and socket. And as a result, with no or little to no cushion, that could lead to a lot of pain. The surgery that I was recommended is called periacetabular osteotomy. This took me a lot of work to pronounce, so please appreciate it. Aside from physical therapy though, this is one of the most common surgeries done on patients, young adults like me, to avoid needing a hip replacement too early on in life. It's very invasive surgery, and through this diagram you can hopefully see here that the main part of the surgery is that they have to cut out part of my pelvic bone and rotate it as to deepen the socket. And it's a very invasive surgery that takes at least 3 months of recovery. A total hip replacement is for severe pain or arthritis, and it's when the damaged joint is removed and replaced by an artificial ball and socket. Usually, hip replacements last around 15 to 20 years, so most people would get them when they're a little bit older. But a struggle of hip dysplasia is that if you get one in, say, your early 30s, you might need another one later because they only last so long. Not only that, but these surgeries can cost $20,000 to $50,000, which is a lot of money. Similarly to humans, dogs are also prone to hip dysplasia. This is my dog Stella, and she's a golden retriever, which means she is genetically prone to getting hip dysplasia. Other dogs like her, golden retrievers, Labradors, bigger breeds like German Shepherds, they are often prone to hip dysplasia later on in their lives, and that leads to arthritis in a lot of them. This is an x-ray of healthy dog hips versus dogs with hip dysplasia. As you can see, it's very similar to that of humans, making them also a great comparison model to humans. This is because they have very similar anatomies, as you can see in the x-rays. The hip socket and the lineup of the socket and the ball of the femur are very, very similar to that of humans. They have many pathophysiological mechanisms of hip dysplasia. It affects them the same way as it does humans, oftentimes leading into arthritis. And dogs are also known to age 5 to 8 times faster than humans, so it's easy to see the progression of the dysplasia as well as progression of different treatments to then compare to humans. Here I created a graph of dogs and humans and how hip dysplasia affects them. As you can see, dogs are much more prone to hip dysplasia because they're genetically to it. It's very common in large breeds, whereas in humans it's a lot less common. This is also why they're a good comparison model, because there are many dogs that we can observe for hip dysplasia, whereas there are a lot less people with hip dysplasia. Over time, both of them can lead to arthritis if left untreated, and the treatment options for both are very similar, including physical therapy, surgery, and oftentimes hip replacement, although it's less common for dogs. As you can see in the highlighted, stem cell therapy is also an option offered for dogs. Stem cell therapy is basically what I'll be covering for the rest of this presentation. But what if I told you that you could inject something into your damaged joint and regenerate your own tissue from your own cells? Well, stem cells do that naturally, but they are very special type of cells in which all cells in your body are derived from. They are essentially the body's repair system. They can divide and differentiate into different somatic cells. Basically, stem cells are used for many types of regenerative medicines because they can regenerate almost all tissues and organs. There are two different types, embryonic and adult stem cells. Embryonic stem cells can differentiate into any cell type, which makes them pluripotent. However, there is a lot of controversy surrounding the ethical concerns with embryonic stem cells. Adult stem cells, however, are multipotent, which means that they have limited differentiation. They're tissue specific, so they can typically only repair tissues of its origin. Adult stem cells is what they use in stem cell therapy. Not only that, but there are a very high concentration of stem cells found specifically in the bone marrow and fat tissue of bodies, and that means that in stem cell therapy, they isolate the dog's stem cells and inject them back into the hip joint. Basically, the process is they take a sample of the dog's fat and isolate mesenchymal stem cells, which are injected back into the hip joint to send out anti-inflammatory signals and repair cell growth to protect the cartilage. They also release growth factors to simulate the same cell repair. And this tends to slow down the arthritis and delay the need for surgery. Most dogs get this treatment around 2 times a year, and the symptom improvement is actually very high. VetStem is one of the biggest biopharmaceutical companies that treats dogs or horses and cats and other mammals with stem cell therapy. Oftentimes, it's used for joint diseases and osteoarthritis. They were founded in 2002, and I explained the process earlier, but basically they collect a sample of fat and it's shipped to their lab to process, isolate, and then concentrate the stem cells. Cells are then implanted back into the pet within 48 hours. They've treated over 6,500 animals, and they continue to do so. There are many logistical advantages to getting stem cell therapy. The first being that it improves the quality of life without being costly or invasive. This is actually the most major point because the alternative is surgery or a hip replacement, and that can cost a lot. Stem cell therapy for dogs is usually $2,500, whereas a hip replacement or surgery can cost up to 4 times more. Unfortunately, it's true that dogs don't live quite long, and so once the arthritis develops, it might be more cost-effective to do stem cell therapy rather than a major surgery. It's also more dangerous for a lot of dogs, especially older dogs, to receive surgery or major reconstructive hip replacement. And according to this graph, stem cell therapy shows promising results for dogs suffering from hip dysplasia and have arthritis. This is, again, from VetStem, and they surveyed many pets and, well, their owners. They surveyed their vets and their owners for quality of life improvement, and over 80% of them have reported a significant improvement in their dog's quality of life. Although the trial sizes are relatively small, the graph also has 3 different date ranges showing how the benefits from stem cell therapy are fairly sustainable and can actually last a very long time, up to 100 days. There are, obviously, many risks and shortcomings when it comes to stem cells. The biggest concern that a lot of people automatically jump to is the rejection of cells. because you're injecting cells back into your body, there's a slight potential that a tumor could grow. However, this is very rare because mesenchymal stem cells have a very low possibility of differentiation, which means that they have low tumor forming potential. The second biggest issue is that it doesn't solve hip dysplasia. The bone structure will still remain the same, but it masks the symptoms of arthritis instead. In fact, VetStem put out this statement stating that it will not correct or tighten the joint. However, it will treat the osteoarthritis generally associated with hip dysplasia. Now leads to the question, stem cell therapy for humans. Can it replace surgery? Although it's true that they can likely alleviate pain and delay the need for surgery, stem cell therapy is not yet an administered treatment to directly target people with hip dysplasia. There are, however, many clinical trials using stem cell therapies to address arthritis. A quick search on clinicaltrials.gov shows that there are currently 0 clinical trials for stem cell therapy being used on patients with hip dysplasia. However, there are 241 clinical trials of stem cell therapy being used on patients with arthritis. Compared to surgery, which directly and effectively fixes the bone structure, stem cells are fairly new science, plus they don't directly target the dysplasia. That means that most people will still turn to surgery. Surgery has up to a 90% success rate. It's been around for a long time, and stem cells have only been around for a decade at most, and it's less effective long term. And also compared to dogs with shorter lifespans, a young adult with a longer lifespan might actually benefit more from long-term surgery rather than short-term pain reduction like you can get from stem cells. I have no arthritis yet, but I do have hip pains and I want to delay the surgery. So maybe in the future with more trials and FDA approval, somebody like me could get stem cell therapy to delay the surgery but still help them ease the pain. Obviously, though, this answers the question. Stem cell therapy cannot and will not replace surgery, but it does show a lot of promise to supplement actual treatments for dysplasia. As I mentioned earlier, FDA approval is one of the biggest barriers for stem cells to be used in a clinical setting for humans. There are 3 clinical trial phases, first being safety, second effectiveness, and third large-scale trials used for accuracy on results and the process. FDA is very costly and very strictly monitored. However, laws for animals are much less strict, which is why you see a lot more trials of people doing stem cell therapy for dogs instead. In addition, hip dysplasia only affects a small population of people. As I mentioned, only 1% of babies have hip dysplasia, whereas investment on clinical trials for stem cells on hip dysplasia is less favored. So that's why there are a lot of trials for arthritis right now, which affects around 25% of adults. So based on the existing veterinary and clinical research, it is true that stem cell therapy may serve as a promising, non-invasive treatment that reduces inflammation and can improve joint function. However, stem cell therapy does not correct or completely change structural abnormalities of the hip joint, as it only regenerates small bits of tissue to support and not entire pieces of cartilage or bone. Findings in many canine studies for arthritis suggest stem cells may delay disease progression, and for humans, the need for surgery for young patients. But continued clinical trials in the future may determine the applicability to human patients as a more widespread form of treatment. Although stem cell therapy is not much of an option for people like me right now with hip dysplasia, and most definitely cannot replace surgery, there's definitely still hope for the future. With further research and testings, like the current ones for arthritis, regenerative medicine, like stem cell therapy, might eventually be used to treat other joint diseases as well and helps people in the same situation as me. Hip dysplasia is one of the many instances in which there is heavy biological overlap of humans with another species that can lead to advancements in our medicine. It's important that the field of comparative medicine and biopharmaceutical science continues to foster for this reason. Thank you so much.
Excellent. Thanks so much, Katie. We have time for a couple questions.
Amazing presentation. I was just wondering, why haven't your symptoms for hip dysplasia showed up until recently?
Oh, good question. This is because I I'm assuming I wasn't really thoroughly checked for hip dysplasia when I was an infant, or maybe I just had light hip instability. Either way, it wasn't a huge problem when I was younger, but I've been putting a lot more strain on my hips since coming here with dance and soccer, so that's why it showed up during soccer season, where I was practicing like almost every single day for 2 hours. That was just a lot for my hips to handle, and that led to heavy inflammation then.
Hi, Katie. I was just wondering, you talked a lot about dogs in general, and I was just wondering, like, what made you focus on dogs and stem cell therapy in comparison to other animals?
Well, dogs are one of the more common candidates used for stem cell therapy, specifically because they're genetically prone to hip dysplasia, whereas other animals might not be like, other animals might not have hip dysplasia at the rate that a lot of the larger breeds of dogs do. It's a lot of biopharmaceutical companies like VetStem, like the one I talked about, do treat other mammals as well, but dogs are by far the more common species to have it. So that's why I decided to focus on dogs as a comparative model.
Any other questions?
Hi, you talked about how embryonic stem cells have some ethical questions surrounding them. Can you talk a little bit more about that?
Yeah. So embryonic stem cells, as the name suggests, there are stem cells that are actually taken from the embryo. So that means that a lot of people are concerned they're killing like potential life. I actually had the privilege of visiting a biology lab and shadowing there over spring break. And one of the people there had done some work with stem cells, including embryonic and adult stem cells in the past. And they told me that for their company at least, they would, for a lot of like egg donors, and they have like leftover like material and like embryos that aren't really gonna be used, like they're gonna be trashed, and that's what's taken. Those are the stem cells that are taken. So I guess from that perspective, it's not as much of an ethical concern because although it's from an embryo, it's not killing potential life because that potential life wasn't really going to be like used anyway. I know that sounds bad, but yeah. But a lot of people are concerned with that because it's like it prohibits the embryo to actually become a baby. Whereas in adult stem cells, it's from your own cells, so you're not really killing potential life. It's just from like fat tissue deposits or the bone marrow. Thank you.
All right, so I'm here up today to do a small presentation on visual BCI. And in case you didn't know, BCI stands for Brain-Computer Interface. This is one of the most cutting-edge technologies in 2026. And because of one reason, let's imagine this scenario. So blindness, people with blindness have two kind of conditions. One's like partly blind, one's totally blind. Let's imagine that we're totally blind. So totally blind means that you don't kind of have light perception, you don't have any idea of what's surrounding you, kind of have no idea of like light, yeah, I just said light, sorry, but like color, form, and stuff like that. Instead, your brain kind of fills you in with random like color pictures, noises, flashes that you would probably see in modern art. But one day, consider one day there's a breakthrough, and the breakthrough is that the scientists start putting some kind of brain chip into your brain, and what they say is that this chip will help you regain your visual sight, and when they turn on the device, the chip, you start, well, the modern art in your brain kind of just fades away, and then you start seeing the world again. And at this point, you're not just only like a normal patient, but you're also one of the first people to actually have a visual BCI implanted. And what I just said is not purely just an imagination. In fact, this is what Neuralink's brain-computer interface called Blindside is attempting to achieve and has been on track to. So, a lot of questions probably, but let's break down the problem first and see what do we need for people to actually see. So I kind of see it as 3 steps: capture the world, process the world, and feel the world. So capturing the world, that could be easily done by a camera. We all know how cameras work, kind of, right? And we have Neuralink's own camera. This is Elon Musk. This is his company, by the way. Him wearing glasses, which are functioning as cameras. And this is processing the world, kind of translate the digital information that the camera captures into information that every digital computer can read. That could be easily done by a computer chip. But the problem is going from transferring the digital information into information that our minds can read. And that's what actually the BCI is about. So to understand how we go from just random digital information like bits in the computer to sites in the brain, we have to understand 2 topics. The first one being action potential, and the second one, terrible pronunciation, rythnotopy. But anyways, let's begin with action potential first. This is how essentially the signal is transferred in the brain. So this thing on the left right here, this is a neuron. It looks kind of goofy, but there's 86 billion of them in your brain, and one of them doesn't do much, but if you have 86 billion of anything, including neurons, you can do a lot of things. And for us, our intelligence, our senses, our consciousness are all built on neurons, 86 billion of them, by the way. And small fun fact, if you want to receive an information in the neuron, it goes in from these dendrites like antennas, goes down, and it passes down here through the USB port, a axon terminal, sorry. And this is a more detailed picture of the neuron. So again, information comes in from here. It kind of touches the blue part, which is the inner membrane, the inner core of it, but it doesn't really go into the nucleus. Instead, it kind of just zigzags on the inner and outer membrane core, and it goes down throughout the axon terminal. And it is able to do so because the inner membrane has a bunch of portals that kind of controls the in and out of information at certain thresholds. And we'll talk about that threshold shortly. But before we even talk about that, have you ever wondered what exactly is the signal we're talking about? So signals could be a lot of things, but in our brain, signal is essentially electricity, or actually, technically speaking, it's a positively charged ion. We call this process not electricity, electrochemical process, impulses. Now the difference is that it's positively charged while electrons are negatively charged. So we have an atom right here, looks like a planet or a system, solar system map. So this is, I think this is carbon, but we have, as you can see, 6 negatives. These are electrons, and 6 positives at the core. These are protons. So when you have the same amount of negatives and positives, you have a balanced atom. This is a normal atom. When you take one electron away, or you take a proton away, it becomes an ion. In this case, we take an electron away, and it becomes a positively charged ion. And being charged means that it creates voltage, which kind of is essentially how it moves on in the cells, in the neurons, sorry. And the idea of voltage is a super complicated, not super complicated, the concept itself is not super related. It's essentially electric potential difference. And in our case, voltage is mainly influenced by the idea of the concentration gradient. So that idea is essentially that if you have a bunch of particles concentrated on the left side, which is highly dense, and you have slightly less populated particles on the right, particles on the left would naturally move to the right until they kind of reach the same balance, so they are equally dense. And that's the idea of the concentration gradient. Think about it as kind of like pressured, but it's going to apply to the thing we're just going to talk about, which is the actual action potential. So this is when a neuron is at rest. It's not receiving any information right now. It's just at rest, chilling. And at this point, we have some sodium ions outside, some potassium ions inside, and all the portals are closed. So nothing travels around. Nothing travels around means that you can have a constant voltage because the pressure, think about it as the pressure of the inside and the outside are the same. Well, not are the same, but they stay constant. And this is where we're at the bottom. So as I said, constant voltage right here, we're resting. Now, when we move on, when we just slightly increase the voltage a little bit, something crazy happens, is that you kind of open up the sodium portal. Now, when you open up the sodium portal, just think about it. If you have kind of a smaller pressure inside than the outside, which has bigger pressure, all the ions would start flooding into the inner membrane, and that's what's going to happen, is that the sodiums would come in, and because they come in, they kind of rise the kind of like impulse or incise voltage, so it peaks at here, and it's going to go up, but the system was like, we have the next shot. We're doing this again, so we can't just let it go on. And what they do is that when it reaches about 40 millivolts, the sodium portal closes down. And now, so you have our voltage is at 40 millivolts. So we have to go back because we just created what's called a signal, an impulse. We have to make another one. So we have to get back there, down there. And what they do is that as the sodium portal closes, the potassium portal opens up. And because now we have a bigger pressure inside than the outside, so the thing changes back, so then the potassium ions would start flooding out. And that causes a significant drop of the voltage until we kind of get back to the same place and both portals shut down. And there we go. You just achieved one action potential, I guess. So what I'm talking about right now, and this is not super, you don't have to memorize this to understand what I'm talking about, but the idea is that if we just increase the voltage at the beginning by a tiny bit, we can essentially trigger our own signal in the brain. Now that's really important. But how would we use that information to help us see? That has to do with another concept I just failed on pronouncing on, retinotopy. So this is idea essentially like graphing the brain, like creating a map for the brain. So we're going to focus on the primary visual cortex, which is the V1 right here. It's at the back of the brain. It's a really small piece. But it processes your brain's visual information. So when you think about how your brain deals with your sight, you might think it's like a black box, really random. Like, I don't know what my brain is doing right now. Actually, your brain makes a lot of sense when you actually see how they work. So this is a scanning of your brain, of someone's brain, reacting to this particular image. So imagine this image being really flashy. It's not very flashy here, I know. But when this person saw this image, their brains reacted like this. This is where the neurons are firing. They're being stimulated by the flash. You see, there's a correlation. Don't they look somewhat similar? So the idea is that, well, the scientists believe that the brain is trying to map what your eyes are seeing. So scientists are like, if brain's doing that for us, can't we just map the brain and then guess what the visual input is going to be like? And that's the concept of essentially of retinotopy. And they chose to do this map, chose to create this map using something called polar coordinates. If you take in calculus, you probably know it's usually used on unit circles. It's essentially, instead of using x and y's, it's using angles and radius as the coordinates. And you might be wondering, why do I have to have such a weird system? Well, that's because your brain has, your body has something called cortical magnification. So I'll show you a few examples right here. Let's particularly look at this one, these two pictures. Those two are really important. So I'll explain. So this picture right here, imagine this is a circle. So imagine staring at the dead center of this thing, and this circle being really flashy again, because if you don't have flash, it just doesn't, it's not simulated enough. Just the circle just kind of like expands and shrinks, and this process takes 2 hours. 2 hours, you just have to stare at the dead center while the circle is like shrinking and expanding. It's a terrible experiment, but we don't have to repeat it again because we've been through that period. So now, after this experiment, you can get a map. Now, how to read this map is that, look at this circle right here. So if this circle is around at the right, red, if the circle is flashing at the red spot, which I think is about right here, where it is, the neurons in your brain fire, the neurons in your brain fired are the red ones. And if it's yellow, it's yellow, it's blue. Now, what I'm gonna say is that, don't you realize that the dark blue part seems disproportionately large compared to how small that dot looks on the map? So that's because your brain, well, you yourself has attention. And when you stare at the middle of your sight, you're staring at someone, you're paying more attention to it. That requires more neurons to process the information. This is a cortical magnification. So your brain actually is somewhat disproportionate. And if you use a normal Cartesian plane to map it, then it wouldn't make much sense because you have a part that's disproportionately large. But luckily, with polar coordinates, we're able to kind of create a graph that makes sense. And after we have a map, neuroengineers be like, oh, now it's gonna be easy. So if I wanna just stimulate, I wanna make this patient see a really flashy light at the bottom, like this part, bottom red, I just have to put like electrodes in this person and stimulate this part of the brain. And similar thing works for yellow, blue, you get what I mean. This is how essentially stimulation or giving blind people vision, this is essentially the first step of that. But there are limitations to this technology right now, because first of all, have you ever wondered how many pixels does your eyes have? You probably think it's a really big number, and you're probably not wrong. Now imagine that under the current technology, you can only put about 1,000 electrodes, imagine them as just like pixels, into your brain, into your whole brain. You only have 1,000 of them. What kind of image can you show? Really, really blurry ones, and they're black and white because current technologies on how can we show colors is underdeveloped. So essentially, you can basically only see like blurry words and numbers, and it's pretty far from actually giving people sight back. Another issue is that this thing is really costly because it's cutting edge, and Neuralink, the company that made it or designed this device, has to make another surgical robot to like do all the implementations and stuff. This is, the developing is spending like millions and millions of dollars. And also your brain's pretty complex. So if you try to just put random electrodes in random positions, like it's kind of gonna mess up your brain at times if you don't do it carefully. And so yeah, there's a pretty high risk to this technology. And here are some of my sources. And yeah, that's it.
So much, Ryerson. We've got some time for some questions.
This is absolutely fascinating, Ryerson. The one slide where you had the person looking at the image that was kind of like a static, like W. Can you explain a little bit more of how like that image kind of shows up? Like you can see it in the scan of the brain?
What do you mean how it shows up?
Like there's like, you said that there's kind of like a correlation between the shapes there.
Oh yeah, these two images are just to show that your brain kind of, like if you see like a V, your brain kind of responds, or neurons in your brain kind of respond in a V shape, if that makes sense. Like the brain is like mirroring what you're seeing. The neurons are at least, yeah. Does that make sense?
Yeah.
Hi, so obviously neurons are responsible for like a lot of our functions. So are there any applications that like any other applications that BCI can do or will maybe one day be possible to do?
Yeah, so Neuralink actually has two products. This one's Blindsight, this one's the newer one. They actually have another one which essentially like functions as, the other one's for like disabled people. So if you can't move your hands, they kind of develop this BCI that plugs into your brain and you can kind of control your computer using your mind, which is another application that's currently under development. Other applications, some say there's some stuff to do with sensory, there's some stuff to do with education, but it's highly uncertain. Like the brain can do so many stuff, but we don't have any actual examples yet.
Hi, I was wondering, in the past, there's kind of been some pushback against the development of medicine for curing blindness and other such disabilities. Kind of what is your response to that, and what do you think kind of the development of this will look like with that?
Yeah, certainly. So this thing actually has raised a lot of ethical issues. One of them is that since it's really expensive, they're concerned that this only goes to like wealthy individuals. And it's kind of like, because you're making your own body like better in some way, and that's like, you know, really unfair for the people who doesn't have this technology. But interestingly, so this technology, this product Blindsight has only done two implementations. They both succeeded. But even though there's like barely any implementations, the FDA approved this technology, so it's actually going to be a product in like 2 or 3 years. And I believe that's because it's in some ways reliable enough.
You mentioned that the electrodes can cause specific parts of the brain to fire to create like an image in the brain for specific like areas. How do these electrodes work, and how do you guarantee that they only target specific parts and create like the image that you want?
That's a really good question. So because neurons are really small, and electrodes, although they're really small also, they're comparatively really big. So the pixel that I'm talking about is actually a pretty big image. That's, if you put it on, like, if you think about a flash on your eye, that's probably how big it is. It's pretty blurry, and well, the Neuralink technicians feel like there's two ways to solve this. Is because it's either you make, I guess, the electrodes smaller, or you just, I guess, plant more of them and like they kind of like overlap each other in some way. But this is highly uncertain, by the way. This is too new to.
This is more like a clarifying question. So you talked about the robots that insert the chips to human brains. You also talked about the electrodes. So I was just wondering, like, what do the chips do? Because they also sound really high tech.
Wait, sorry, I didn't hear your question.
No, I was just asking about, because you showed an image of the robots that Neuralink spent a lot of money to make to insert chips into human brains, right? Is that related to the electro part of this, or is that something else? What do the chips do?
So the robot itself is more of an engineering topic. I don't have much information on it, sorry. But if you're talking about the chip itself is not anything fancy. It's just a typical computer chip that does functions for this particular product. Does that make sense?
All right, I'm gonna make it quick. Kind of along the lines of Coco's question. We all know like the brain is a very fragile part of our body, and the neurons are very intricate. And then like this method's idea of like using external stimulus to kind of signify parts of the brain. Are there any concerns in terms of like these like signal stimulus kind of impacting other region of the brains and creating like missed signals and miscommunications? Because like all the neurons and pathways are very like complicated and crossover in the brain.
Yeah, so there's definitely a risk. I'm not sure if there's any accident that has occurred, but this is why some other companies who also try to do BCIs do like, I don't know, they don't try to implement chips inside the brain. Instead, they put the tray on the skin of the brain, and they kind of do like a, they kind of control, like create electrical voltage that I just talked about from the outside of the brain. And there's benefits and disadvantages to that technology compared to this, mainly because the outside getting into the inner core is super hard. But as you see, this one has a slightly bit of more of a risk.
Thank you so much, Art.
As you may hear every day at the end of chapel, life is short and we do not have much time. But for many people, that time is shortened by something they cannot control, organ failure. Every year, millions of people around the world suffer from failing hearts, kidneys, livers, and lungs. And for many of them, transplantation is their only hope, yet the number of available donor organs falls far short of the need. But what if we didn't have to wait for a donor? Today, advances in the medical field are bringing us closer to a new solution: 3D bioprinting, the ability to use a patient's own body to potentially create an organ. And what once sounded like science fiction is rapidly becoming a frontier in modern medicine. How serious is organ failure? Millions suffer from life-threatening illnesses which often result in organ failure. Organ failure occurs when organs can no longer function to sustain life and regenerate the necessary tissues. It's caused by sepsis, chronic diseases, or a traumatic injury. Therefore, organ failure remains a major cause of morbidity due to its limited treatment options, making a challenge in modern medicine. Statistical survival models show that organ failure increases the risk of death by 6 times. And at this critical stage, surgery through transplantation becomes the only life-saving option. Over here is an image of 1 million people. It's already a lot to take in, the image stretching farther than you can count. But why am I showing you this? Well, if you saw in the previous slide, over 850 million people suffer from kidney diseases and heart failure. And heart diseases alone account for 32% of global deaths. Now imagine multiplying this image by hundreds. When you try to visualize it this way, the scale becomes almost impossible to comprehend with so many human lives being affected directly. Currently, the replacement of organs is done through biological and mechanical approaches. Biological organ transplantation works by replacing the failing heart with a healthy donor heart, and it's the current leading treatment for end-stage organ failure. Biological organ transplantation can also restore full function of the normal organ. On the other hand, mechanical organ transplantation supports organ function until a donor organ becomes available. This, in turn, mitigates long donor waiting lists. And these two methods dominate the clinical field because they're the only solutions capable of sustaining life once severe damage has occurred. Unfortunately, both solutions face many challenges that limit their efficiency. Biological transplants face 2 major limitations: limited donor availability and immune rejection. Now, you might understand how organ shortages are caused by a lack of donors, but you might be wondering what immune rejection is. Immune rejection is when the immune system destroys the cells of the new donor organ and damages the tissues so it can't be used. This becomes important to note later on. So as a result, many people die before a suitable organ even becomes available or after the transplantation itself. Mechanical organ transplantation have their own issues, including fatal symptoms like stroke, thrombosis, gastrointestinal bleeding. These devices are also expensive and only temporary solutions until a real organ becomes available. In the US, only 49,000 transplants were done out of 108,000 people waiting last year. And this disproportion between the high number of cases and limited replacement options further highlights the need for a new approach without introducing any of these fatal complications. And that brings us to the solution: 3D bioprinting organ structures. Now, historically, medical models go back to ancient civilizations where clay was used to study human anatomy. If you fast forward to more than 1,000 years later to the 1980s, Charles Hull patented and invented 3D printing, a revolutionary technology that uses plastic to make objects, usually in a layer-by-layer method. Now, 3D bioprinting is exactly what it sounds like. It's unsurprisingly derived from 3D printing and creates biological structures like tissues using a combination of living cells, specifically stem cells, and polymers, which is basically a big molecule. This combination makes up a special ink called bioink that goes into the printer. The created structure then incubates so the cells can mature and grow. This ink also has stuff called growth factors that enable the development of the cells. Growth factors are basically proteins that are found in stem cells that activate processes like regeneration or giving the cells their specific function depending on the organ they form. And this is called differentiation. It's kind of like getting a job. And while this technology is still under development and clinical trials, research progress shows its potential as a future clinical solution. But if it is a potential solution, what will actually set apart 3D bioprinting from traditional methods? To show the differences, I'm going to compare the two traditional methods of transplantation with 3D bioprinting. Organ transplantation has been around for decades and saved millions of lives, but it still has two big issues. First is immune rejection, which I already mentioned is when the body sees the new organ as foreign, signaling to destroy the organ. Second, transplantation itself is dependent on donor availability, resulting in waiting times and delayed treatments. This also leads to higher costs for surgery, as a kidney, the most frequently sought out organ, can go well over $500,000. In comparison, 3D bioprinting can produce organs at high volumes, eliminating dependence on donor organs completely. And by using a patient's own cells to make tissues specifically based on their genetic makeup, this improves integration with the body and reduces immune rejection rates. In contrast to mechanical organs, 3D bioprinting offers a more long-term solution as they're made from living cells and not metal. And they're also designed to imitate the structure and functionality of native organs. Therefore, this biological compatibility reduces the risk of blood clots, strokes, and other fatal complications. As 3D bioprinting inches its way towards clinical adoption, its rapid production rate can contribute to lower costs as well. While it's good to know the promises bioprinting holds, it's equally important to understand the techniques that make it possible. And while there are many complex techniques, I'll briefly introduce three of the major ones that are layer by layer based: extrusion, inkjet, and laser based. Extrusion bioprinting uses a nozzle and is the most widely used technique, working by mechanically forcing the bioink with all the cells and biomaterials through something like a syringe to stack up into the desired structure. This technique is very cheap and can print with multiple different types of high cell density bioinks. And high cell density means that the cells are more packed together and can interact better with each other, improving the structure and functionality of the tissue. However, the negatives are slow printing speeds and low resolution, meaning it lacks the precise level of details seen in real complex organs like the heart. Additionally, during the process, shear stresses can act on the cells, and this can rupture the cell membrane, leading to cell death and eventually the death of the organ. So a balance between high resolution and high cell viability is necessary to create complex functionality. But for now, extrusion is very useful for scaling larger tissues and even smaller organs, some of the applications which we'll see in a later slide. Inkjet is the first bioprinting technology developed and works like a standard inkjet printer, but uses a modified printhead with droplets of bioink to make 3D structures with high precision. Inkjet bioprinting offers several advantages, including fast printing speeds, medium resolution, and affordable cost, making it well suited for printing small structures the size of micrometers. However, it cannot print with high cell density bioinks due to nozzle clogging, so the environment isn't the best for the cells to develop during incubation. So the structures stay relatively simple and small. Like a normal inkjet printer, inkjet bioprinting is generally done through thermal and piezoelectric methods. Piezoelectric essentially uses electric charges to deposit droplets of bioink with pressure. Thermal inkjet bioprinting in particular is the most popular and works by heating the bioinks at high temperatures, like 200 Celsius, to form vapor bubbles that propel bioink droplets out of the nozzle onto the receiving platform. Last but not least, laser-assisted bioprinting, or lab, was originally developed for computer chip production. The way this process works is by focusing a laser on an absorbent material over a glass plate, creating high-pressure liquid bubbles that push bioink droplets onto the receiving substrate. It's kind of like inkjet. Compared to inkjet-based and extrusion-based bioprinting, however, there's no nozzle involved, so there's no nozzle clogging, and lab is able to accurately print with high cell density, high resolution, and high cell viability. However, it's still experimental and extremely expensive. Also, the amount of laser transfer per pulse is small and makes printing speeds very slow, preventing lab from being used in scalable production where speed is necessary. Now let's take a look at some of the latest achievements in 3D bioprinting. In 2017, the laser bioprinting technique used stromal cells, which are just cells that support the structure within organs like the bone. They combined these cells with the bioink and put it into a bone defect in mice, rearranging cells around in the proper locations so the bone could regenerate itself. In 2019, blood vessel networks were printed by arranging endothelial cells and using a bioink called Pluronic F127. First, endothelial cells are basically the cell types you see in your own blood vessels. Pluronic F127 is a biomaterial with a gel that acts as a temporary scaffold to maintain the structure shape during printing. Now, the network of blood vessels is called vascularization. These networks supply oxygen and nutrients while removing waste, making them essential for cells to survive. And without it, cells are deprived of oxygen, rapidly dying and eventually killing the entire organ. The same year, an entire heart was made by Tel Aviv University with spontaneous beating and vascularization. 2 years later, inkjet bioprinting was also used to make an alveolar barrier model, a membrane within the lungs. This was a huge achievement because lungs are responsible for respiration and gas exchange. 4 types of lung cells were used in bioink, and the model made was actually very similar to lung environments, allowing for gas exchange of oxygenated blood. In 2022, volumetric bioprinting, something I didn't talk about, used light waves to solidify the bioink in a matter of seconds all at once, rather than by using layer by layer. And last year, Penn State researchers made a new bioprinting technique called HITS Bio that is 10 times faster than all current methods and also has a high cell viability over 90%. And while some of these works are not directly related to organ transplantation and more toward regenerative medicine and drug testing, it shows how we can already have spatial organization of cells and create parts of an organ, functions of an organ, and even blood vessels for organs during extended periods of time. And although there has been several new advancements, bioprinting has a few issues that still prevents its transition from experimental to clinical usage. And the reason why these obstacles arise is because traditional human organs are unsurprisingly more complex than skin or muscles, consisting of more than one cell types and specific arrangements in order to coordinate function. For example, the heart has 11 different cell types, totaling to billions of cells to allow beating and blood circulation. But right now, we just lack the technology to organize all these cells into the exact locations for functionality. Vascularization is another huge obstacle. To be specific, in living organs, the blood vessel networks have to be between 100 to 200 micrometers away from a cell to properly nourish it. Any thick tissue cannot fit the vessels in the right proximity and kills cells and eventually kills the organ. And though there's a bunch of development on creating blood vessels that I discussed before, it's unknown whether these vascular networks can interact with the existing circulatory system of the patient. So you might not have remembered all this information, which is okay. To refresh your memory, bioink is what goes into the printers to create structures and is made of polymers mixed with stem cells. While stem cells are cells that differ depending on the type of function of the organ, the polymers are called hydrogels. And gels are very important in bioprinting because they act as a scaffold like when you build a house. As you can tell by hydro, these guys can hold lots of water to mimic the soft texture of tissues and encapsulate the cells. The perfect hydrogel must balance biocompatibility and organ characteristics. This makes sense because the organ cells must be able to interact with the body by exhibiting normal organ behaviors like sensation, tensile strength, and elasticity. These hydrogels can be divided into two types, natural and synthetic. Natural polymers are biodegradable and from nature, having stronger biocompatibility and better cellular interaction. They're very useful because they're similar to biological molecules and have a lesser risk of immune rejection since the cells are more adapted to the body. However, natural polymers lack strength and can break down during printing. Synthetic polymers have the opposite problem. They're made of chemicals and have better control over organ characteristics and can be molded easier, but do not have as strong of a cellular interaction as natural polymers. So reproducing the full range of the organ properties and biocompatibility is difficult because existing materials either lack the structural integrity necessary or hinder biological function. As you can tell from this big mess of different cells, printing techniques, and organs, bioprinting requires highly controlled environments, sophisticated equipment, and specialized cells. Commercial bioprinters can cost over $1 million depending on its capabilities, and harvesting billions of cells of a large organ is time-consuming and unfeasible. Scalability is a problem as organs require high throughput and mass production. The high cost can exacerbate wage gap between different social classes because where wealthier patients or countries can gain access to this new medical therapy while others are left behind, raising concerns about accessibility in healthcare. Fortunately, researchers are working on stem cell expansion. If you don't recall, stem cells can regenerate along with differentiating. So we can exploit that by increasing the rate at which it regenerates. As a result, the cost is projected to decrease once it becomes produced at high volumes and used widely. Once passing preclinical development, the next stage is getting approval from a bunch of regulatory agencies listed above. Most of these agencies require loads of evaluation, and to establish the commercialization of bioprinting organs, you need several different bodies that focus on several different areas like medical devices, pharmaceuticals, and tissue engineering. Unfortunately, there is no regulatory body that has released any framework pertaining to 3D bioprinting. But such regulations are necessary due to ethical concerns associated with safety and human rights in the usage of living stem cells. There are three types of stem cells: embryonic, adult cells, and induced pluripotent. Embryonic stem cells can become any cell type in any organ and are from embryos, leading to ethical concerns over human destruction. Adult stem cells are restricted to creating cell types in the specific tissues they live in, but are not as controversial since they're already developed. So, induced pluripotent stem cells combines the benefits of both and are adult cells genetically reprogrammed to become more like embryonic cells, so it can become any cell type in the body while also being ethically compliant. But even induced pluripotent stem cells aren't free of ethical issues because of autologous and allogenic. So autologous are stem cells from the patient themselves, while allogenic is from another donor. And autologous stem cells reduces immune rejection because they're from the patient themselves, but can cause tumor growth. Allogenic, on the other hand, is cost-effective, but raises questions on the identity of the patient. And even though we need testing to mitigate safety and ethical risks, human trials with these stem cells are restricted, and animal testing is less favorable, rapidly being pushed out. So why am I even talking about 3D bioprinting organs if the challenges are many and the technology is still developing? Well, that's because the problem it aims to solve is even bigger. Hundreds of millions are affected by organ diseases, and thousands of patients die each year waiting for transplants that never even come. Even though organ transplantation rates are rising and reaching record highs, it barely reaches 50% of the need every year. That's why it's so crucial to have more research to expedite the developments on bioprinting and target the organs most needed for transplantation. The push for research is shown to be efficient because a lot of other challenges are being addressed already. One key area that is being developed is the printing techniques. Future bioprinters are becoming hybrid, combining different bioprinting techniques and using multiple cell types to better replicate the architecture of organs. These hybrid printing methods are also utilizing AI through machine learning and deep learning to use the most appropriate bioprinting technique for each part of the organ structure, and dynamically switching between high resolution and a high speed printing to scale objects with precise details. As a result, the future of 3D bioprinting is not grim, but actually becoming closer and closer to making its way towards clinical application. Overall, 3D bioprinting has shown considerable promise in tissue engineering, and existing challenges can and already are being overcome. New creations of artificial skin, bone, ears, cornea, lung, and heart highlight how researchers are actively developing more and more complex structures and even beginning to implant simple structures into humans and animals. Continued innovation along these lines points to a more ethical and efficient preclinical process where research integrates biology, medicine, and engineering, offering a future where patients can save their valuable time and allow for millions of people to live longer and healthier lives. Thank you.
Great. Thank you so much, Joseph. We'll take a couple of quick questions.
Thank you, Joseph. This has been great. Where is this research primarily happening right now? I mean, where if we wanted to study this, where should we go?
So you can, like, a bunch of universities are studying it, for example, like Penn State that I talk about. And also, like, just like for example, like Texas Medical Research, I think they're, like, using bioprinters to, like, study, like how they can be used for regenerative medicine and drug delivery and also drug testing. And so, yeah, you can go to, like, any university, and a lot of individual researchers or research groups will study this, especially in the biomedical field.
How long do you think it's going to take for this to become, like, mainstream?
So not immediately, but right now it's still in development, but in the future, in like a few decades, it has potential to, like, significantly reduce or even replace the need for donors.
Hi, I was wondering if the surgery process of implanting, like, these artificial or quote-unquote artificial organs would be any different from implanting, like, a human donated organ.
Well, yeah, as I talked about before, bioprinted organs can reduce the rate of immune rejection because the cells in that tissue of the organ are already well adapted to the body and from the patient themselves. So it will definitely reduce immune rejection rates, and yeah.
Hi, Joseph. I just wanted to ask if this bioprinting method could be used to solve, like, other problems that humans have, such as, like, missing limbs or other, like, cosmetic surgeries where they might be missing, like, tissue from, like, accidents or.
I'm not sure about missing limbs, but it can definitely solve, like, missing tissues, and it already has. Like, I think in China or in South Korea, people have already implanted, like, ears. So, yeah, it can definitely solve, like, issues with tissues.
Excellent. Thank you so much, Joseph. Thank you all so much. You've been an incredible audience.